Welcome to our physical science class. Today we are starting an exciting journey into the universality of physics laws. This concept means that the rules governing motion and energy here on Earth are exactly the same across the entire universe. Whether we are looking at a falling apple or a distant galaxy, the same principles apply. By the end of this unit, you will see how these elegant laws connect everything around us. Let us begin. For our first lesson, we have 3 clear learning targets. First, you will learn to describe Aristotle's ancient views on natural and violent motion. Second, you will be able to explain how Galileo concluded that falling objects experience uniform acceleration. Finally, you will analyze projectile motion, defined as objects flying through the air, by looking at horizontal and vertical movements. Keeping these targets in mind will show you exactly what to focus on today. Let us get started. As we move through our first lesson, we will focus on one big, essential question. How did Galileo's experimental approach change our understanding of motion compared to the ideas of Aristotle? This question matters because it marks the birth of modern scientific inquiry. Before we compare these two thinkers, let us define what physics actually is. To understand physics, we must look at where it fits within science. Science was once called natural philosophy, which is the study of the natural world. It is split into life sciences, like biology and physical sciences, which study non-living things. Physics is the most fundamental of these physical sciences. It does not just look at specific materials, but instead deals with matter, motion, force, and energy. For example, physics explains how a giant space station can orbit our planet. Now, let us examine the branch of physics that is most apparent in our everyday lives. We begin our physics journey with mechanics, which is the study of forces and motion. This is the part of physics that is most visible in our daily routines. In this lesson, our focus is on kinematics, defined as how objects move without considering forces. We will look at motion in one dimension, like athletes running along a straight track. Every move you make, from raising your hand to walking, follows these rules. Let us look closely at how we describe this motion. Let us start with a quick demonstration. Imagine dropping a pen and a piece of paper at the same time. What do you think will happen? Most people expect the pen to reach the ground first, and in normal air, that is exactly what we observe. The paper flutters down while the pen falls quickly. Now consider this question. What if we tape the paper tightly to the pen and drop them together? Suddenly they fall at the same time. This observation hints that something other than gravity is responsible for the difference. Let us compare how 2 great scientists viewed motion. Aristotle believed that objects naturally seek a state of rest, and that motion only occurs when a force is applied. He divided motion into natural motion, based on an object's composition, and violent motion, caused by external pushes. For almost 2,000 years, people also believed his idea that heavier objects fall faster. Think of a heavy rock falling faster than a feather. This ancient view was highly influential, but not entirely correct. To better understand these ideas, let us look at the life and work of Aristotle himself. Aristotle was born in Macedonia and entered Plato's famous academy at the age of 17, studying there for 20 years. He later tutored young Alexander the Great before establishing his own school. Aristotle's great life goal was to organize all existing knowledge of the physical world, much like Euclid did for geometry. He collected specimens and made detailed observations to classify the natural world. This systematic approach, meaning a structured way of classifying information, became the framework that sparked the rise of Western science. Although his specific ideas on motion were eventually disproved, his dedication to organizing knowledge shaped human history. Now let us fast forward to the 16th century and see how Galileo challenged these long-held views. Galileo challenged Aristotelian views of motion by supporting the Copernican idea that Earth moves. Unlike Aristotle, Galileo argued that motion is not determined by an object's composition. Instead, he showed that motion can be described using measurable quantities, such as time and distance. Through careful observation and experimentation, Galileo demonstrated that scientific claims must be tested rather than accepted based on authority or tradition. Galileo Galilei was born in Pisa, Italy, and began his studies in medicine before turning to mathematics and motion. Through careful observation and experimentation, he challenged Aristotelian ideas that had dominated science for centuries. Galileo showed that heavier objects do not fall faster than lighter ones, and used a telescope to discover moons orbiting Jupiter and imperfections on the Sun. These findings supported the Copernican idea of a moving Earth and changed how scientists understood the universe. Galileo began by challenging Aristotle's belief that heavier objects fall faster than lighter ones. Legend says he dropped 2 spheres of different masses from the Leaning Tower of Pisa to show they landed at the same time. Whether or not he performed this exact experiment, Galileo used rigorous logic to prove his point. He argued that air resistance is the only reason some things fall slowly. For instance, a sheet of paper falls slowly because of the air, not its weight. This was a revolutionary shift in thinking. Let us examine how Galileo corrected the ancient view of falling objects. In normal air, a feather falls much slower than a coin. Aristotle assumed this was due to their weights, but Galileo realized that air resistance, which is the drag force exerted by air on moving objects, was the real cause. When air is removed from a chamber, a feather and a coin drop together will hit the bottom at the exact same instant. They both accelerate at a constant rate of 9.8 meters per second squared, regardless of their mass. This demonstrates that in a true vacuum, gravity acts on all objects equally, causing them to speed up in perfect unison. Since we now understand vertical freefall, let us see what happens when we throw an object horizontally. Let us explore projectile motion, which is the motion of objects flying through the air. A fascinating case is horizontal projection, which is launching an object parallel to the ground. Imagine dropping a ball straight down while simultaneously throwing another ball sideways from the exact same height. Surprisingly, both balls will strike the ground at the same time. This occurs because the vertical pull of gravity is exactly the same for both objects. The sideways velocity of the thrown ball has zero influence on how fast it falls. This crucial experiment proves that horizontal motion and vertical motion occur simultaneously and are completely independent of each other. Let us look at what happens when an object is projected at an angle to the ground. This action creates a symmetric curved path, known as a parabola. This curved trajectory, meaning the path followed by a flying object, is a combination of two independent motions. First, there is horizontal motion, where the object moves forward at a constant speed because no horizontal forces are acting on it. Second, there is vertical motion, where the object rises against gravity, slows to a stop at its peak, and then accelerates downward. Because these independent motions happen at the same time, they produce the classic curved paths of a thrown baseball or a kicked football. Let us look at a practical example of how these theories differ. Imagine a hockey puck sliding across a frozen pond until it finally stops. How would Aristotle explain this? He would tell you that the puck stops because it is natural for moving objects to seek rest. But Galileo, and later Isaac Newton, had a completely different explanation. They argued that the puck would actually slide forever in a straight line if nothing stopped it. The only reason the puck stops is friction, defined as resistance forces caused by surfaces in contact. This means coming to a stop is not natural for an object, but the result of an external force acting on it. Let us analyze the physics behind a spectacular slam dunk. When a basketball player leaps into the air, they become a projectile following a curved path. At the very top of their jump, their vertical velocity slows down to nearly zero before they start accelerating back downward. However, their horizontal speed remains constant as they move forward. This combination of constant forward motion and extremely slow vertical movement at the highest point of the curve creates the illusion of hang time. The player seems to hover in the air, but they are simply following the elegant, predictable laws of projectile motion that apply to any launched object. This summary table brings together all the key contrasts between Aristotelian and Galilean physics. Under vertical motion, we see that Aristotle was incorrect in saying weight determines falling speed, while Galileo was correct in showing that all masses fall equally. For horizontal motion, Aristotle wrongly believed that motion requires a constant force. Galileo correctly asserted that an object will keep moving in a straight line unless an external force acts on it. Finally, for projectile motion, both agreed that medium resistance exists, but Galileo was correct in analyzing the curved path as two independent horizontal and vertical motions. This table clearly shows how early philosophy transitioned into experimental science. Let us fully answer the essential question we introduced at the start of our lesson. Galileo's experimental approach transformed our understanding of motion by moving science away from pure speculation. Aristotle believed that a continuous force is necessary to keep an object moving and that heavier masses fall faster. Galileo challenged this by conducting careful tests, proving that all objects fall with the same constant acceleration when we ignore air resistance. His discoveries showed that the physical world does not behave randomly or according to abstract philosophies. Instead, motion can be measured, analyzed, and predicted using universal physical laws. This work laid the foundation for modern physics. To conclude our first lesson, here is your exit ticket pop quiz. You have 3 questions to answer. First, according to Aristotle, why do objects move or fall? Second, what did Galileo discover about objects of different masses in free fall? Finally, why do a dropped ball and a horizontally thrown ball hit the ground at the exact same time? Answering these questions in your notebooks will show that you have mastered our learning targets for today. Thank you for your hard work.